Greetings, calculus students. Mr. Winter back at you here. I'm going to create a couple of videos today. One, I'm gathering some of you still had a little bit of trouble with the geometric series test and the nth term test. So I'm going to make just a really short video just kind of talking about how they work and such like that with a couple examples. And then this afternoon I'll also post a homework help video where I actually take on some of the questions that you guys have told me you're giving you trouble from the homework itself. Let's get started. First, geometric series test. Geometric series, what is it? Quite simply, let me change colors here. If I have a series, which means I'm going to add a bunch of numbers, let's say I've got something like this. Let's say I go 5, and then I'm going to add 10, and then I'm going to add 20, then I'm going to add 40, and I'm going to continue on and on forever. That is a geometric series. Why? Well, because each term differs by what's called a common ratio. Like here, to go from 5 to 10, I multiply by 2. To go from 10 to 20, I multiply by 2. To go from 20 to 40, again, I get a common ratio of 2 in each case. So a geometric series basically means, gosh, that's a really ugly looking R here, but bear with me. It basically means you're adding an infinite number of terms, and then each term is, the subsequent term following it is found by multiplying it by some common ratio. Now what the geometric series test says is basically this. For a geometric series with ratio r, if the absolute value of r is greater than or equal to 1, the series diverges, which means basically it's just going to get really, really, really stupid huge up to infinity, or really, really crazy small to like negative infinity. This one right here is a classic example of a divergent series. If I keep adding on terms like 5, 10, 20, 40, 80, 160, 320, 640, and so forth, what I hope you see is that the series just keeps getting bigger and bigger and bigger. I'm just adding bigger and bigger numbers. It's never going to approach any value. It just gets ridiculously huge and approaches infinity. That's what I mean by divergent. Now, the second part of it is if the absolute value of the ratio is less than 1, the series converges to, this is S sub n equals a over 1 minus r. S sub n means the sum of n terms. R is your common ratio, and a is your initial term. Let me kind of walk you through how this works. So here I have a geometric series. You say, well, it's just adding the number 3 each time. Yeah, but to get from term to term to term, in each case, it's times 1, times 1, times 1, times 1. So basically, this is a geometric series with a ratio of 1. Now, what's going to happen here if I keep adding 3, 3, 3, 3, 3, 3, 3, 3, 3? Well, it's going to get really, really huge, and it's going to be infinite. It's just going to never stop getting larger. So it approaches infinity, or we say that it not converges. Let me erase that. That's really bad. That diverges. So let's put that in context of the geometric series test. If I look right here at number 1, it says if the absolute value of the ratio is greater than or equal to 1, the series diverges. So here, I take the absolute value of r, which is the absolute value of 1, which is 1, which is greater than or equal to 1, which tells me the series diverges. It just gets ridiculously huge. Next one. This one is a geometric series as well, only this time I'm multiplying by negative 1. So I get a series whose ratio is negative 1. Now again, just intuitively, you can see what's going to happen. If I have a -5 and I subtract 5 more and I subtract 5 more, if I just keep subtracting 5, what's going to happen is this is going to approach negative infinity, which also means it's going to diverge. Now again, with respect to the geometric series test, which says if the absolute value of the ratio, which in this case is the absolute value of -1, which is 1, which is greater than or equal to 1, which means the series diverges. So whether the ratio is positive or negative really doesn't have an effect. It's just whether it's going to go to positive infinity or negative infinity if it diverges. So that's kind of what the absolute value does. It takes the whole sign of it out of play. I'm not worried about whether it approaches infinity or negative infinity. I just care, does it get really huge or does it stop at some point? So in each case, if I were to go out, like 5,000 terms, like here, I'm just going to be adding another 3. Here, I'm going to be adding a -5. It keeps changing the value of the function, of the series, making it either bigger or smaller. Let's try something like this. Here, again, I have a geometric series. And to get from term to term, I multiply by 2. So I have a geometric series of ratio 2. Again, according to our geometric series test, I want to find the absolute value of the ratio, which is the absolute value of 2, which is 2, which is greater than or equal to 1, which means I'm going to keep adding bigger and bigger numbers of consequence. It's going to get infinitely large, which means the series diverges. Now this one's a little different here. So what if I take here? Here, to get from term to term to term, I have a ratio of 1/2. Half times 1 is half. Half times half is 1/4. Half times 1/4 is 1/8. So if I take the absolute value of my ratio, that's the absolute value of half, which is half, which is less than 1. Now let me go back. And we know that if the absolute value of the ratio is less than 1, I know, number one, that it converges, but more importantly, I know what it converges to. It converges to a over 1 minus r. So I know that that absolute value of the ratio is less than 1, so I know it converges to, and let me clear a little space here. Let me erase. It converges to a over 1 minus r. So my a, still erasing. Let's try that again. I'll get this figured out eventually. Okay. So a is my initial term 1. So my sum of n terms is a over 1 minus r, which is 1 over 1 minus, and my ratio is half, which makes 1 over half. And when you take 1 and divide it by a half, it's the same as multiplying by the reciprocal 2. So it's really 1 times 2, or 2. So in other words, if I were to keep adding on terms here, it's going to get no larger than 2. Now, for some people, that might freak you out a little bit. You say, but you're adding something. It's going to change the value. Well, yeah, but look at what's happening to these values. They keep getting smaller. Like right now, I'm at 1/8. Can you imagine what number I would have if I were to add like the 1 billionth term, it would be like 1 over 2 to the 1 billionth power. It's basically like saying that eventually I'm going to be adding something that's really, really close to 0 if I go out far enough. And adding 0 doesn't change the value. So there's a limit as to how big or how small it's going to get. That's what I mean by convergence. Nth term test, one of my favorites. It's really easy. One thing I am going to tell you, it is the nth term test for divergence only. It cannot be used to determine convergence, so please keep that in mind. And it basically says this: if the limit as n approaches infinity of a sub n is not equal 0, then the series diverges. That basically means this: if I'm going out and out and out, and I keep adding numbers, and all these numbers keep getting big to where they're not 0, it means that I'm adding something of consequence. I am changing the value. It diverges. So, and then this test is inconclusive if the limit is equal to 0. Just because you're like adding something close to 0 out there does not mean it converges. And when I teach you guys the integral test, I'll show you how that kind of works. But it can be used to tell very quickly if something diverges. Couple examples here. I have the series from 1 to infinity, 5n plus 2 over 7n minus 5. If you feel so inclined, and I'm going to be honest, I don't ordinarily, but I'll do it this one time. What this means is, first I'll plug in 1. So 5 times 1 plus 2 would be 7. 7 times 1 minus 5 would be 2. Next term I would plug in 2. 5 times 2 plus 2 would be 12. 7 times 2 is 14 minus 5. That's 9. Let me do one last one. Plug in 3. 15 plus 2 is 13. And then 7 times 3 is 21 minus 5, 16. And so forth. These are the terms I'd be adding. Now, what I can see is that the top keeps getting bigger by 5. The bottom gets bigger by 7. Okay. What I don't see happening here is this. I don't see that when I add these terms, it doesn't look like it approaches 0. So intuitively, I think this is going to diverge. But to be sure, I'm going to do this. Nth term test says I want to find the limit as n approaches infinity of an. What's an? That's an. It's the formula for the series. Now, hopefully you recall that when we're doing a limit at infinity, I'm only worried about the highest power of the variable. So like this 2, this 5, they don't really cancel, but they're insignificant. So that gives me limit as n approaches infinity of 5n over 7n. Now I can actually cancel the n's, which gives me 5/7. And last time I checked, that does not equal 0. So in other words, what's happening is if I go out 1 billion terms, I'm still adding something of consequence. I'm not adding 0. So my series is getting bigger and bigger and bigger, which means it diverges. So since the limit as n approaches infinity of the series an does not equal 0, then the actual series, it's at 5n plus 2 over 7n minus 5, it diverges. It's just going to keep getting bigger and bigger and bigger. Okay? Number 6, and please don't call that exclamation point. That is factorial. Factorial in a nutshell basically means this. Like if I say 4 factorial, that means 4 times 3 times 2 times 1. You basically just take the integer itself and then multiply, reducing by one number each time until you get to 1. So here's the idea. I want to take the limit as n approaches infinity of 3n factorial over n factorial plus 5. A little thing I can tell you about factorial is that when you do this, numbers get really big really fast. Like 4 factorial, if I were to multiply this out, would be 24. 5 factorial would be that same thing. It would be 4 factorial, but times another 5, it makes 120. 6 factorial is 720, and it gets really big really fast. So this 5 I would regard as insignificant. Factorials get way bigger faster than adding 5 does. So then I get limit n approaches infinity of 3n factorial over n factorial. Factorials cancel, I get 3. More important than that I get 3 is what I don't get. I don't get 0, which means my series diverges by the nth term test. One last one here. If I take this one, again, I'm going to go limit n approaches infinity, 5n plus 3, 2n squared plus 7, and those are insignificant. I get limit n approaches infinity, 5n over 2n squared, reduced by a power of n, or by a factor of n. I get limit as n approaches infinity, 5 over 2n, which is like saying 5 over 2 infinities, which approaches basically 0. So what happens when the limit as n approaches infinity of an equals 0? I have no clue. It may converge, it may diverge, I don't know. The nth term test is inconclusive. So as we add more tools to your toolbox, I'll show you ways to where you can figure that out. But for now, I cannot tell what it does. I hope that helps. I will put some homework together later on this afternoon. Thanks.